Hello, this is lecture 15. I apologize for recording this lecture late. I was sick for a few days. Not sure if it was corona or something else, but I'm back now. What we will do in this lecture is we will kind of continue discussing momentum and things related to momentum and conservation of momentum. And we will look at some consequences of conservation of momentum in first half. And in the second half of the lecture, we will look at some sample problems, and we will see how the conservation of momentum and energy can be used to solve it. So we will start with the center of mass, with the concept of center of mass, which is one of the concepts that naturally arises from conservation of momentum. And to see why that's the case, we can think about a very simple interaction. Let's say we have two astronauts in space. They push against each other, and let's say this astronaut has twice the mass of that astronaut. Then we know that they will both start moving, and we also know that the second astronaut, which is lighter, will move twice as fast. And this follows from the conservation of momentum, because in the beginning the momentum of the two was 0, and after they interact with each other, the total momentum has to stay 0. So this astronaut will move with velocity v, and it has mass 2m, so the momentum is v times 2m. And this momentum has to be canceled out by the second momentum. And so if this astronaut has half the mass, it must have twice the velocity for the total momentum to remain at 0. If you are twice as light, you will move twice as fast. So every second, this first astronaut will, let me call this astronaut A, this is astronaut B. Every second, astronaut B will be moving twice as far from the origin as astronaut A. And then it's easy to verify that if you take the x coordinate of astronaut A and you multiply it by its mass, this thing will always be equal to the x coordinate of astronaut B times his mass. And basically from this, it follows that there is this imaginary point in between these two astronauts. We will call this point the center of mass. And as these astronauts are moving, the center of mass remains here. Now, what happens if we have more than 2 objects? So let's say we have 5 objects. I will draw 5 objects here. No, they could be 5 asteroids or any other objects that interact between themselves but don't interact with anything else, anything external. And if they only interact with each other, and if the forces obey the 3rd law of Newton, then it's also easy to check that, maybe not easy, but the math works out so that as these objects move, so for example this object could move to here and this object could move to here, they will all be moving, but their center of mass will stay where it is. So if it was here at the beginning, then the center of mass will stay here no matter how these objects move. And the center of mass is perhaps not that difficult of a concept, because we all have intuition about the center of mass from our everyday lives. So for example, if you have 2 objects, and if they have equal mass, then their center of mass is exactly in the middle of the line that connects them. But if one of the objects, let's say this object is heavier, then the heavier object will pull the center of mass towards itself, so the center of mass will be closer to the heavy object. This is kind of the intuition, and the formulas are also not that complicated. If you have a bunch of points that have different masses, then, so for example, in this case, let's say this is 0.1, 0.2, 0.3, 0.4, 0.5, then their center of mass, to find their center of mass, what you have to do is you have to draw x and y coordinates. So this is my x-axis, this is my y-axis. You have to take x and y coordinates of all points, and then the x coordinate of the center of mass is x1 times m1 plus x2 times m2 plus, so on and so forth, x5 times m5. So what we're doing is we're adding the x components and we're weighting them by mass. So whichever point has more mass, that point will have more say in where the center of mass is. And then we divide this by the total mass, which is m1 plus m2 plus so on and so forth, plus m5. And for the y component of the center of mass and the z component of the center of mass, you have exactly the same formulas. But now in the summation, instead of x coordinate, we use y coordinate or z coordinate. Otherwise, formulas are basically identical. So these formulas are given on slide number 3. And now what I want to do is I want to look at a specific kind of problem that is somewhat similar to one of the homework problems that you will have. In this problem, we have 3 objects. We know their masses, we know where they are. And what we have to do is we have to find the center of mass. Okay, so this is slide number 4 on my slides. So what's happening here is that we have 3 objects. So one object is here. It weighs 100 grams, so that's 0.1 kilos. The second object is here, 4 centimeters away. That's 0.4 meters, 0.04 meters. And this object weighs 150 grams, that's 0.15 kilos. And then we have this third object above. This object is 3 centimeters away, so 0.03 meters. And this object weighs 0.75 grams, 0.075 kilograms. And so the question is, find the center of mass of these 3 points. So first of all, before we start solving this problem, let's think about where we expect the center of mass to be. The center of mass, should be kind of intuitively should be somewhere inside this imaginary triangle, right? And if all 3 objects were of equal mass, then you would expect it to be kind of in the geometric center. But since they are not of the same mass, so these bottom 2 are heavier. This one is the heaviest. We kind of expect the center of mass to move somewhat in this direction, toward the down right direction, southeast direction. So let's see if that's indeed the case. So first of all, I need to draw my x and y axes. What I will do is I will draw my x-axis like so. This will be my x-axis. And I will draw my y-axis like so, pointing up, so that the origin is on top of this one of the points. Now, what I will do is let's call this point A, let's call this point B, and let's call this point C. What I will do is I will write down X and Y coordinates of A, B, and C. Let's start with the A. So A is at the origin. Both the X and the Y coordinates are 0. Now let's look at B. This is B. B is on the x-axis. Its x coordinate is 0.04. Its y coordinate is 0. And now let's look at point C. Point C is up here. I can project it to x and I can project it to y. And if I do that, then the x component will be 0.04 and the y component will be 0.03. Okay, so now let's find the x and y of the center of mass. I will write down the equations. The x of center of mass is x1 times m1 plus x2 times m2 plus x3 times m3 divided by m1 plus m2 plus m3. And for the y, I have exactly the same formula, except all the x's are replaced by y's. So let's compute some numbers. What I will do is I will compute x center of mass for you, and I will leave it up to you to compute y center of mass, because it's basically it's exactly the same thing, just with different numbers. So x center of mass is x1 times m1, that's 0 times 0.1, plus 0.04 times 0.15 plus 0.04 times 0.075. And I need to divide this by the total mass, which is 0.1 plus 0.15 plus 0.075. So let me quickly punch these numbers into my calculator and I will get back to you. Okay, so when I crunch these numbers, I get 0.028 meters. So from here to here, I have 0.04 meters. Exactly midway is 0.02 meters. So 0.028 is slightly to the right, kind of as expected. Now, I will leave it up to you to compute y center of mass. And once you know y center of mass, you know exactly where the center of mass of these 3 particles is. Now, in this case, we have 3 particles. You could have as many as you wish. If you had 17 particles, that would mean more computations. But in principle, as long as you have discrete particles, computing the center of mass is always easy, in a sense that there is this well-defined formula that you can use for x, y, and z components. But sometimes, we don't have discrete particles. We have extended objects. So, for example, you could have a stick like this, or something like this. And when you have extended objects, things become slightly more complicated. Instead of taking sums, you will now have to take integrals. Now, for EP1, I don't really want you to do that. You can read about this if you're interested. We will only attempt to find the center of mass for, so-called symmetric objects, for which it's kind of obvious from symmetry arguments where the center of mass is. What I mean by symmetry arguments is that, for example, if you have a rod, something like this, and if this rod is uniform, then it's kind of clear intuitively that the center of mass of this rod has to be exactly in the middle. And if you have a square or a rectangle, then again, based on symmetry arguments, it's kind of clear that the center of mass of this rectangle, if it's uniform, has to be in the middle. You know, there are other objects like a circle, for example. If you have a circle which is uniform, then you know that the center of mass is here. You know, for these symmetric objects, we can identify their center of masses without doing any integrals. In one of your homework problems, you have something that looks like this. You know, there are 3 sticks, stick number 1, stick number 2, stick number 3, that make this C-like shape. And to solve this, what you can do is you can invoke exactly these symmetry arguments. You can say, okay, I will split this into 3 objects, object number 1, object number 2, object number 3. For each object, you can imagine, for each object, since it's symmetric, you know exactly where its center of mass is. So for example, this stick will have its center of mass here, exactly in the middle. Same for this stick, same for this stick. And then you can pretend that all of the mass is at this point. And now instead of 3 sticks, you have 3 points. You know exactly where they are. You know what their masses are. So what you can do is you can just use those equations that we had on the slide before. Yeah. Now you have another problem in your homework that's even more complicated. You have a shape that kind of looks like this. So it's like a square with another square cut out of it. I'm now on slide number 5. So what do we do with this? This kind of shape doesn't have any obvious symmetries. So there are a few things that you can do. So one thing that you can do is you can subdivide it into 3 different rectangles. So you could put an imaginary partition here and another partition here. And then you would have 3 rectangles, rectangle number 1, rectangle number 2, rectangle number 3. For each one of them, you now can guess exactly where the center of mass is because they are symmetric. So each one of them will have a center of mass exactly in the middle. And then if you can compute the mass of each of these pieces, then again, you are now reduced to, instead of having this complicated shape, you now have 3 points with known masses and known locations. There is another way of solving this problem, which is, which is arguably a bit simpler from the technical point of view. So this is so-called method of negative mass. So what you can do is you can pretend that you have two squares. You can pretend that one square is this full square without any parts being cut out. And then you can pretend that there is a second imaginary square in here that has a negative mass. Okay. And so the significance of this negative mass is that putting something on top that has negative mass is kind of like cutting this piece out. And now things are also easy because you have 2 squares. For each square, you know exactly where the center of mass is because they are highly symmetric. So now you have 2 objects, you know exactly where they are, you know how much they weigh. The only thing is that this red cutout kind of has negative mass. So you can think about this shape as two squares, one with negative mass, one with positive mass. And then you can use the familiar formula, which is x, the center of mass is x1, m1. And this time you have to use a negative sign here because you have a negative mass. So let me go back. This is m1 minus m2. So look at your homework. These are the first three homework problems. Try to solve them before Friday. If you cannot solve them before Friday, I will have my Zoom room open from 12:30 to 2:30. So please join, and we will go over this again during the help room session. So this is as complicated as we will get when it comes to the center of mass. And for the second half of the lecture, what I want to do is I want to go back to the conservation of momentum. I want to look at some sample problems that require both the conservation of momentum and conservation of energy, and I want to solve them so that it becomes hopefully clearer how these two conservation laws interact, when to use conservation of momentum and when to use conservation of energy. So, just to briefly remind you how these things work, this is on slide number 6, a short summary. The momentum is usually almost always conserved unless you have external forces. Actually, it is conserved exactly when you don't have external forces. And momentum is a vector, so direction matters. Energy is not always conserved. When you have a collision, when your objects collide, or when you have an explosion, something explodes, usually you either lose or gain energy. When you have collisions, you usually lose energy because some part of energy goes into creating sound waves and deforming those objects. And when you have explosions, you usually create energy because there was some chemical energy that was trapped in chemical bonds, and because of the explosion, that energy got released. So energy may or may not be conserved. You should never assume that it's conserved unless there is something in the problem that tells you so. But momentum is, in the absence of external forces, momentum is always conserved. Okay, so I will pause this recording now, and this is the end of the first half. In the second half, we'll go over those 4 sample problems, and I will try to solve them for you step by step.